This is lesson 53 of our A-level physics no-nonsense lessons, all about conservation of momentum. Imagine getting 53 lessons into an A-level physics course, or any physics course, and only just learning about conservation of momentum. But here we are. So this is a principle. Now, where it comes from, I'm not going to go into 𝗟𝗶ৃ's theorem to talk about where conservation of momentum comes from. It's a consequence of symmetry. So 𝗟𝗶, spell it right, 𝗟𝗶's theorem. If you want to look it up, you can do. I think that's how it's spelt, or it's probably an O with a strange line through it somewhere. 𝗟𝗶's theorem, which talks about how different conservation rules are the consequence of different symmetries. I'm not going to do that. Go look that up if you're interested. What I'm going to talk about is just the fact. The fact is that in a closed system, momentum is always conserved. So what do we mean by a closed system? A closed system is one where there is no transfer of energy or matter in or out. Now that's what we would call an isolated system in chemistry, but and they call a closed system something slightly different. We can call it an isolated system if we want, but it's very fun to watch chemists go red in the face and start puffing and getting angry, so let's call it a closed system because it winds them up. So a closed system is one where there's no transfer of energy or matter in or out of the system. We can imagine that our system is encased in what's called an adiabatic barrier. So it's a barrier that doesn't allow the transfer of energy in or out, or matter in or out. An adiabatic, not diabetic, that's something different. And so I'm going to put here sort of enclosed, adiabatically, put letters back to front, diabatically. I might have made that word up with the suffix at the end, but there we go. So we're only looking at closed systems here. Now in closed systems, we don't transfer energy in and out, we don't transfer matter in and out. So what? So actually within a closed system, the total momentum in a closed system is constant. What do I mean by that? I mean that the rate of change of momentum in a closed system is 0. Now I've got to keep emphasizing this is for a closed system only, because obviously it's possible to change the momentum of a body. If it wasn't possible to change the momentum of a body, we could never change anything's motion. Momentum is just another way of describing motion. There's another word we could use for motion. We talk about velocity, but we can also talk about momentum. So the total momentum of a body can obviously change because its motion can change, but that's not in isolation. So another way of saying this is momentum can be transferred, is transferred. How many R's in transferred? There might be too many there. Transferred from one body to another when the bodies interact. Now, in classical physics, that interaction is a push, a pull. Any of the old classical forces, we've got tension, friction, air resistance. We can even have things like the gravitational force, electrostatic force, and so on. But we can go down into the particle physics domain, and we can look at interactions between particles with the strong nuclear force and with the weak nuclear force. And this is still true in those situations. In fact, part of the discovery of the neutrino was based on the idea that it must be, in a closed system, the conservation of momentum must be observed. So where does the rest of the momentum go? And then we discovered the neutrino, observed the neutrino sometime after it was proposed. But it was proposed due to conservation of momentum. Now, the difference between conservation of momentum and conservation of energy is a scalar. Momentum is a vector. So we are not just conserving the magnitude of the momentum within a closed system, we're conserving the direction of the total momentum in our closed system as well. So momentum is a vector. Remember we studied vectors, and I said at GCSE it was an irritated bolt-on extra that no one really cared about. And in A-level it's tremendously important. Well, here we go. In A-level it's tremendously important, and I'm going to keep on mentioning how very tremendously important it is, because it is. Right, let's just move this up a bit, because I have the space, and I might as well give myself the space for later on. Okay, so what? Momentum is always conserved. Well, that means that when we look at a collision between two bodies, we can say that momentum is being passed from one body to another. And I'll talk about collision just because it's easy in classical physics to talk about collisions. But any interaction between two bodies, this is what we're going to get, of course. Any interaction between two bodies, even if it's a non-contact interaction. It's not just contact interactions. I've run out of room. Let's move that. Oh, I do love the fact I can just move things around on the whiteboard. It is lovely. And we're going to copy that and stick that over here. So we're going to have three situations: before collision, during collision, and after collision. Let's just label them. Before, during, and after, being inconsistent with my capitalization. So we're just going to look at this in terms of momentum, just in terms of momentum, nothing else. Let's suppose that has that amount of momentum. Momentum is a vector, and so we are representing that amount of momentum just like that. They collide. There's a transfer of momentum from one body to the other, and it could be the case that all of the momentum is transferred over, and then that body on the left becomes at rest and the body on the right carries on like that. So that is one type of collision. That's just put this like this, and let's just say example 1. That's one type of collision. But that's not the only way things could have happened. Or as the young people say, it's not the only way it could have gone down. We could have, let's just draw this underneath. Same situation now. Let's draw it like that. Yeah, let's give us a little bit of white space in our notes. There we go. Let's do this as example 2, and let's modify it. So in example 2, perhaps not all of the momentum is transferred over for some reason. So before, we've got the situation we had before. Now during, perhaps what actually happens is we transfer more momentum. Oops, didn't mean to go back into the notes. There we go. We transfer more momentum. So let's get my eraser out. And let's now have a bigger orange arrow. Is that possible? Well, absolutely yes, it is. That we can have that shoot off like this. This is momentum of body 2, but only if the momentum of body 1 is in the opposite direction. So I'm now going to cheat somewhat. I'm going to drop this down here. If I had a ruler, I'd use a ruler. I don't have a ruler, so leave me alone. Let's copy that, pop that here, like this. And so what we're going to do is have an amount of momentum which is that much. Now you can see very clearly what I'm trying to do here. That is my momentum of 2, because my momentum of body 1, sorry, because my momentum of body 1 plus my momentum of body 2 still will equal that total momentum P. Let's move some things around. Okay, there's momentum body 2, just like body 1, sorry, just like that. I'll just draw it there. And so if I go, oh, the P, oof, let's get rid of that. Oh, it's a mess. There we go. So this is the total momentum that we're trying to copy. That's the resultant. So P2 plus P1, it equals P. You can see very, very clearly. I'll actually erase these in a second. But you can see it very, very clearly that P2 plus P1 is P. So we still have the same amount of momentum we had before when we add up the momenta of our bodies after the collision. I will just write that in words underneath it. So I'll just write down here, P, as a pen, not a highlighter. I will write down here, P is equal to P1 plus P2, but this is definitely vector sums. And this is critical because in your A level, they don't tend to handle vectors very well. So you might have to write down something like P equals P2 minus P1 in order to get marks. You'll have to show that minus symbol to show that you understand that P1 is in the opposite direction to P2. And the magnitude of P2, subtract the magnitude of P1, is the magnitude of P. And then after the collision, of course, the total momentum is exactly the same as what we had. It's just they're now going off on their merry way, carrying that momentum with them. So that one goes that way, and that one goes that way after the collision. And we can look at any situation like that. So what's actually happening is we are transferring momentum. In the first example, which I think is the easier one cognitively to visualize, the momentum that's held by this body is passed over to this body, and that body trundles off with that momentum. It's being given away. In the same way as we learn energy in early on in our school, we treat it like it's some sort of like a substance, even though it's not. We can do the same thing with momentum. We can treat it like it's some sort of substance, even though it's not, that's passed from the first body to the second body. So from body 1 to body 2. So that's body 1 and body 2, body 1 and body 2, body 1 and body 2. And it's the same thing in the second case, except it kind of looks on the face of it like we've created some momentum because P1 is bigger than P was, but we haven't. We've transferred momentum to P2 into the second body, into body 2, and an equal amount of momentum in the opposite direction into P1. Have I worded that right? Well, the total adds up to the same thing, so I think I've worded that right. So there is that transfer. So momentum transfers over, and it's the same thing happening in example 2, and so on and so on. So what? Right, okay, so the amount of momentum that's transferred, we'll just look at the first example. We are losing P. So the change in momentum is going to be, and I'm going to do this in a different color, the change in momentum in example 1 is just going to be, try and line that up, the change in momentum is just going to be that. So let's move that. And I will actually move all this down to give myself a bit more room. Did it? Ah, missed a bit. Give myself a bit more room because it's important. So we've got a change in momentum. Let's just do this. This is my delta P1. And I've got a change in momentum for the second body. Here it is. And that's going to be delta P2. And that's why our second body moves off with the same momentum that the first body had. So you can see what's happening there is these two have to be equal to each other. And if we look at the second example, it's going to be a little bit more complicated now. It doesn't need to be more complicated. I could use the copy tool and then just change the color. I don't know why I didn't do that before. So I should be able to move that down there, change the color to red. Oh, yes. So the change in momentum of body 2 is that amount. That is the momentum that's been transferred to body 2. So what's been transferred to body 1? Well, exactly the same amount. It's just going to be in the opposite direction. So that, and let's get the pen out. There we go. I really hope these diagrams help make it clearer what's going on. So the change in momentum of body 1 is just going to be P1 subtract P. So that is equal to P1 subtract P. And P is to the right, so when you subtract it, it's to the left, and that's exactly what we see. And this one here is just going to be P2 subtract what it initially had, which was 0. Subtract 0. And they are equal. Those changes in momentum are equal. We don't create momentum. We don't destroy momentum. So the amount of momentum that's transferred is the same. Now, if I add delta P1 and delta P2 together, it will be equal to 0. In both of these cases, in all cases of collisions or any sort of interaction, if I add the two changes of momentum together, it will be equal to 0. So there's some important points, and I'm going to make a little note of that in the box to the left. So number 1, duration of collision for body 1 equals for body 2. They have to be the same duration. Body 1 can't be pushing against body 2 and be in contact with body 2 and have body 2 not in contact with body 1. If body 1 is touching body 2 is touching body 1. That's how contact works. So the duration of collision is the same. And then we could say that the delta P1 is equal in magnitude to delta P2 in magnitude. So that's why I'm using these vertical bars. That's what they indicate is magnitude, delta P2. The amount of momentum that's transferred is the same. Now remember that force, it was equal to the change in momentum divided by time. And we've just said that the duration of the collision for body 1 is the same as for body 2. And the magnitude of the change of momentum for body 1 is the same as for body 2. So if delta P1 over T is equal to minus delta P2 over T, that is true, then F1 is equal to minus F2. The magnitude of F1 is the same as the magnitude of F2. That is true. That is the essence of Newton's third law. Not simply, oh, every action has an equal and opposite reaction, which is the most disgusting and vomit-inducing wording of Newton's third law ever. It doesn't work. It causes misconceptions. It misuses technical physics terminology. It does more harm than good. Yes, it's catchy and all students can recite it, but they don't know what it means. It is an abomination in education. No, not that. We're going to be looking at what are the natures of these forces. So if we're saying that momentum is always conserved, Newton's theorem says that for a closed system it is. If momentum is always conserved, then the consequence of that is that there's no such thing as an isolated force. Because any interaction between one body with another, there's the reciprocal force in the other direction. The interactions come in pairs. You can't just have one object pushing another one without the other object pushing the first one back. And the magnitudes of the forces are the same and they're in opposite directions. But that's only two of the things that relate these two forces. There are in fact 6 things that relate these two forces. 6. I mean, some resources will talk about 5. There are in fact 6 things that these pair of forces have about them. Sometimes they're in common, sometimes they're differences, but we'll go into this list in just a second. If you ever see 2 forces in a free body diagram, the 2 forces are acting on the same body, then that's not an interaction. We've already seen that internal forces cancel out. So we're talking here about the forces between 2 bodies, and they always come in pairs due to conservation of momentum. So some of you watching this, the penny will now be dropping. So let's look at the 5 conditions. Actually, I'm going to call them 6 conditions for Newton's third law. Conditions for Newton's third law. So let us suppose that you've got a diagram. It's not a free body diagram because there's multiple different bodies in the diagram. And in this diagram, there happens to be 2 forces written down, 2 force arrows. And you look at them and think, are they a Newton's third law pair of forces? Well, there's some things to check. We've got the classic one. They will have equal magnitude. If the 2 forces, magnitude, if the 2 forces have equal magnitude, they might be a Newton's third law pair, but they might not be. Are they in opposite directions? If they're not, then they're obviously not Newton's third law pairs, because momentum has to be conserved, and momentum is a vector. And there's another thing which is difficult to see on these diagrams, but the forces are interactions between 2 bodies, and the interactions happen along a particular line of action. Again, that's linked to the vector nature of forces and the vector nature of momentum. So we could say that the 2 forces are along the same line of action. In other words, if we've got an object and it's got a force, another object is a force like this, and the lines of action are not the same, they're not a Newton's third law pair. That's not to say those 2 forces aren't there. They might be there because of some other reason, but they're not a Newton's third law pair, which means each of those forces will have a corresponding paired force acting as well. Number 4, they happen at the same time or same duration and instant. So it's all about time. Now that one often gets ignored from the list, but I think it's important to include it. The forces, as you can see in the example I've scrolled so you can see, You can't have object 1 pushing 2 without 2 also being in contact with 1 and pushing it back. They're in contact for the same duration, and the contacts happen at the same time. But what about non-contact forces? Well, that's still true for non-contact forces, and it's the reason why Newton's third law doesn't work in relativity, which I'm sure we'll get onto much, much later in our A-level course. This is classical physics, and it's only classical physics. When we move on to relativity, relativistic physics, more modern physics, relativity is 120 years old now, but we still think of it as new. When we get on to 120 years at the time of recording, by the time you listen to us, it might be much later. That's new physics, according to exam boards. In that, Newton's third law doesn't apply. Newton's laws of motion are wrong, or is they're not the best model, should I say. Number 5, the forces act between 2 bodies. And that's a giveaway. If the 2 forces you have identified in a diagram are both acting on the same body, they may well be there, but they're not going to be a Newton's third law pair. And each of those forces will have a corresponding force acting on another body. Not necessarily the same body for each of those forces either. That is important because very often Newton's third law gets mixed up with Newton's first law. People will see an object and it'll have 2 force arrows acting on it, and they'll go, oh, okay, well, we know this one must be the same magnitude as that because of Newton's third law. No, the object might be in equilibrium because the forces balance, but there's no reason for them to be the same. It just happens to be the same. You could just as well have an object that's not in equilibrium because the 2 forces acting on it are not the same magnitude, or even the forces acting on it are in different directions, or even different lines of action. We've got a couple somehow, or even only 1 force acting on the object at all. So when you see 2 forces acting on an object that happen to balance, you're looking at Newton's first law, looking at equilibrium. You're looking at momentum for an object not changing. But we're talking about momentum for a closed system not changing, and that system contains more than 1 object. And the last point, these 2 forces are in fact the same force. This Newton's third law pair of forces is an interaction, and the interaction goes both ways, but it is an interaction. It is a single phenomenon. That's what it is. And that means that the forces are of the same type. So a non-contact electrostatic force is paired with another non-contact electrostatic force. A push force is paired with a push force. Tension is paired with tension, and so on and so on and so on. These are the 6 conditions for Newton's third law. Very often, as I've said, condition number 4 will be missed off the list, and you'll hear about 5 conditions. If at all. I mean, sometimes people don't give you this tick list, and you'll just be told something disgusting like action and reaction. What does that even mean? What is a reaction? Reaction implies some sort of causal dependency. The action came first, the reaction came later, but actually they happen at the same instant in time. So that's just not true. So let's think of some examples, and then we can use this checklist. So let's think of the first example for Newton's third law and check and see if 2 forces are a pair. The first example is going to be someone sat on a chair. So here's my attempt at drawing a 3-dimensional chair. There's the legs, and then there's the back of the chair there. And we're going to draw the person sat on this chair, minding their own business. Here they are. Here they are. Let's sat on this chair. They've got a head as well. There they are. And we're going to look at the forces acting on this person. And we know that there's a force of gravity acting down on this person. Is there a force acting up on them? Well, yes, there is. And it's a push force from the chair. And that push force from the chair, sometimes called R for reaction force, sometimes S for support force, will be the same magnitude. So are they a Newton's third law pair? Well, they have equal magnitude and they're in opposite directions. But they're not necessarily the same line of action, although the resultant forces will be if we're not causing a couple on the object. So yeah, let's go with that as well. Are they the same duration and instant? Well, I suppose they will be in this particular case. Otherwise, the chair would be collapsing and stuff. So I guess so. What about acting on two bodies? No, doesn't act on two bodies. The same type? No, one's gravitational and one is a push force. So no, these two forces are not a Newton's third law pair. They're just not. Let's look at another example. Let's take the example of a spring and a mass. So a mass spring system. And we've got the mass is being pulled down and the spring is applying a force pulling it up. Are they a pair of forces? No, because they're acting on the same body. But that does mean that each of these forces will have a pair. So the spring is being pulled down with the same force that the mass is being pulled up. Well, that means the spring would be accelerating down. Well, no, because the top part of the spring is being pulled up with the tension in the spring. Are those two, T and F, a pair of forces? No, they're not a pair of forces because they're both acting on the same body. But that means that we can have a tension force on the bit of spring next to it of equal magnitude. And you can do that all the way up the spring until you get to the top part that's holding the spring in place. And that's being pulled down with the same force that the spring is being pulled up. And so on and so on and so on. So where's the force to this one? We had the person sat on a chair. They had weight. We've got this slotted mass. This has got weight. Where's the paired force? The reason why students don't see it is because the Earth is too massive. If the Earth had less mass, we lived on some sort of small asteroid, we'd start seeing what the paired force is. We jump in the air, we still have our gravitational force acting on us down, and there's an equal magnitude force acting on the Earth towards us. There's equal magnitude, excuse me, opposite direction, same line of action. They would both happen at the same time. One's acting on the person, one's acting on the planet, and they're both gravitational forces. So that would be Newton's third law satisfied. Right, I've got one last thing to talk about, and that is how we represent collisions algebraically. Collisions algebraically. I don't know if it's got an A in there, but we'll see. Collisions algebraically. So let us consider a collision between two bodies, body A and body B, or body 1 and let's go body 1 and body 2. Let's use A and B. Let's use A and B. So collision, let's say collision between A and B. Between A and B. Doesn't matter what the nature of that collision is, any sort of collision, this is what we've got. So the momentum of A before would be equal to the mass of A multiplied by the initial velocity of A. And we can use that sort of notation all the way through. Now what we'll say is that the momentum of A before added to the momentum of B before, that total momentum must be equal to the momentum of A after plus the momentum of B after. Some momentum may have been transferred from one of the objects to the other. So some momentum may have been transferred from A to B. So B has more of the momentum, A has less. Bearing in mind momentum is a vector. Doesn't really matter. But the total is the same. So we could say that MAUA plus MBUB is equal to MAVA, using the A and V notation, MBVB. And that is always true in classical physics. Now here's the problem. The plus is there because we're adding vectors. However, exam boards are not very good at dealing with vectors, and so they may well have on a diagram UA in one direction, UA in one direction, and UB in another direction. And in that case, you'd have to make that a minus sign to indicate that you have appreciated that UB is to the left. As long as you stick with the convention, it's a nice idea in your paper to write down what your convention is. As long as you stick with the convention, then it should be fine. But you will have to do this not as a vector sum, like this is. The pluses are only there because these are vector sums. You're going to have to do them as scalar sums and differences, where the directionality has been taken over with the diagram, and you're putting in pluses and minuses to add together the scalar quantities and still have everything conserve. Should I fill in here? PA after equals MAVA. Do you need the rest of them written down? I don't think you do. And so on. It's the notation we're using. Right, now that's a lot of variables there, but if you want to solve any collision problem, all you're going to be doing is figuring out what the missing quantity is and just doing algebra. Sometimes it takes a bit of work. Sometimes you'll have some rather nasty equations that have some simultaneous equations, but that doesn't matter. It's going to be the same thing, which is just using these two equations. Using this one equation, sorry, the one in blue, this conservation of momentum equation. Okay, let's just draw a box around it because it's quite important. It's at the bottom of the notes, but that doesn't make it any less important. We've covered a lot this lesson, haven't we? We've talked about conservation of momentum and collisions, and then moved on to Newton's third law, and then a conservation of momentum equation written out. So we're going to dance around a bit, but I think there's enough in there for you to be getting on with. So next lesson, we'll be looking at different types of collisions, and I hope you'll join me then. Bye-bye.